I now have enough information to know that L is bigger than C. This right here is IR, and I need to know that angle right there. Well, it's a little bit tricky. Tangent of phi is the opposite of the adjacent, IL minus IC over IR. (42.017 minus 0.1866 divided by 1.98. It's probably 80 something degrees or 1.5 radians. .55 radians.
(1.52).
1.52. And so my last formula here, IPS, is equal to 42.045 amperes times the cosine of 314.16 radians per second times time minus 1.52. And again, I know it's minus because it's lagging. And so now when we plug in our time of 1.234 seconds, and we're now about to find out how much rounding that hurt us.
Why did you flip it? So why'd you make it I sub L minus I sub C?
Because I know, because when I was doing the phasor diagram, I had no idea which one was bigger. And so I just picked that one to be bigger, to draw it out. It turned out that I sub L is significantly larger than big I sub C. And so that's why I know it's lagging. If I hadn't done that, let's suppose I had gone with just I sub C over I sub L, then those would have been flipped. And then I would have had tangent of phi is equal to something negative. And on the calculator, it would have given me a negative angle, so I would have just done plus that negative angle. I will tell you, on say the master set problem, which is particularly hard, on the master set problem, if you get to that point and you're just off by a minus sign at the very end, it would be such an incredibly minor deduction. All right, so what do we get for IPS?
2.01879.
That does not feel right. Yeah, no, I'm not buying that. Unless the other things are wrong.
Negative 40.61.
Negative 40.61?
60.
60. That would make more sense. If you're ready to subtract 1.52?
Okay. I wanna check what I did wrong.
Now notice, now I picked horrible numbers. Sorry about that. However, we have another check at this point, because these are the instantaneous currents. At this one moment in time, we have the current coming out of the power supply, which is 40.6 amperes in the negative direction. So whichever way is the negative direction, we'll just make this way positive. So the current's going this way at 40.60 amperes. The current going across the resistor, negative, that's 0.6101 amperes. The current across the capacitor is towards the junction, the bottom junction, at 0.1775 amperes. And for the inductor, we had a negative 39.97. So if I think about this junction right here, I have 40.6 coming in, plus this 0.1775 coming in. Do these add up to the ones coming out? Kirchhoff's junction rule holds. So 40.60 plus 0.1775, that's the current that's flowing into this bottom junction. The current flowing out, 39.97 and 0.6101. Ideally, they will match, but you know, there's all sorts of significant figure issues involved here. That silence of just stunned awe.
Can you explain the direction of the current?
All right, so there's what's the positive or negative direction? You know, it's oscillating back and forth, so I just picked the positive direction. So I said positive direction's that way. So positive direction, the current's going to be flowing like that. Negative direction is flowing like that. In the lab, you'll have two leads for the AC, it floats back and forth. You're just going to arbitrarily pick one of them to be positive and one to be the negative side. Even though the voltage will switch which one's the higher one, but that choosing which one's positive, which one's negative, makes setting up the sensors easier. So I had IPS of negative 40.6. Since I said positive current was flowing that way, that means the 40.6 is flowing this way. For the resistor, negative 0.6. So positive this way, negative 0.6 going that way. And then similar for the inductor, we got a negative, which means it's flowing in the negative direction. And then the capacitor, we had a positive that's flowing in the positive direction. Is that sufficient? Mm-hmm. Okay. Other questions?
Suppose we did a lab on this, or are we doing a lab? But, like, what would be the reason for the currents to not match?
Oh, of why these would be off?
Yeah, like,
It'd be purely rounding.
oh, even for the lab, like if we did it?
For the lab, for the lab, part of it is the omega value, you're getting a very similar value for all your angular frequencies. And odds are they're not gonna be exact, they'll probably be accurate to potentially 1 decimal point or 2 decimal points. It'll be 300 and, somewhere around 370 point something radians per second. And so there's gonna be a certain amount of leeway there, which is gonna mess you up at the 5th significant digit. Maybe 4th or 5th significant digit. So that's gonna mess it up. Also just statistical fluctuations. I mean, because you're gonna get a whole bunch of data points and then it's going to curve fit the cosine. Now, one place which, if you're looking for it, it's very obvious when it messes up. Sometimes when you've got a bunch of data points like this, for some reason the LabQuest gets into this spiral and goes, oh, this is the best fit, like this. And you just have to go, yeah, that's not right. And then you, instead of doing a curve fit for the whole thing, you do a curve fit for a smaller part of it, and it eventually straightens itself out. So if you're not paying attention, that's really gonna mess you up.
So it's not like internal resistance of something?
That is, considering there's one part in the lab where if you get 1% error, you've probably done something wrong. There, at the very end of it, I did it, I got 11% off for the very last calculation. And I don't think I ever resolved what caused that 11% error, but that was the largest percent error for the entire lab. Which is one of the reasons I do the lab, is just so that you have the experience of a lab with really good results. Where 11% you're going, man, something's off there. As opposed to 11%, yeah, we did it right. Did I answer your question?
Yeah.
Okay. Other questions?
Can we use like phasers to measure the efficiency of a circuit? Like if a certain current is lagging behind where we wouldn't want it to lag? Like what exactly does the phasor diagram represent?
It represents the actual, each phasor represents the voltage and the current. The instantaneous value is the projection onto this axis right here, where that angle is omega t. And so that, it is a representation of, the length represents the amplitude, and the projection of the x-axis represents the instantaneous value. So as this rotates around, you'll see that the instantaneous value fluctuates back and forth. That's what the phasor, it's just a visual way of, another way of looking at it. I know that my answer was generic, but.
So suppose like if there was a way of measuring any of those values, then we could plot a phasor diagram from the measured values?
Yeah, so in the lab, when you, at some point you do a phasor diagram on it, but mostly you're pulling the equation. So you get the data points, you're measuring current coming off going through the resistance, and you get an equation, and there'll be some phase shift. So you'll get that, and then from that, you could plot a phasor if you wanted to, where that would represent the magnitude. So you set up some scale for current. And then the phase shift sort of tells you the starting point. But the phasor diagram that you do in the lab is based upon theory for an LC circuit, and then you'll match it to what you're finding experimentally. All right, I think we've had about enough of this practical stuff. Let's get to some other stuff. Unless there's another question. All right. Chapter 38, or whatever the relativity chapter is.